Okay, so this is Calculus 3 again, and we're going to be dealing with finding We're going to be dealing with finding the distance from a point to a plane. This is chapter 12 problem for us. So I think most people in America use the same book, so hopefully this should be chapter 12 as well for you all. And we just had a test on this about a week ago. So we're given a point not on the line, and then the equation, or not on the plane, and an equation of the plane. So what we need to realize is that we'd label this as being S. And so this is a point not on the plane. And then this would be our equation of the plane. So that would be 6x plus 3y plus 2z, and that's 12. And let's go over the distance formula, what we need for distance. So to find the distance from a point to the plane, that is going to be equal to the magnitude of PS and the dot product V over the N over the magnitude of N. So the normal vector to the plane over the magnitude of the plane, and we're going to do the dot product of this. So doing this, what we need, let's see what we need. We have S, so S we're good, S is right here. We don't seem to have N, but if we do, we can find the magnitude, and we don't seem to have P, which is a point on the plane. But we can find that, and the only reason that it may not seem that way is because you have to know what makes up the equation of a plane. Now, the equation of a plane in standard form would be written, well, here it's BAX plus BY plus 2, or plus CZ, and that would be equal to 12. Now, what is important about these letters, A, B, and C, is that that is what makes up, these coefficients of the variables here are what makes up the normal vector, which would be A, B, and C. And I think standard form, this is written as some D, something, and that should be vector notation there. So because this is our normal vector, pulling the coefficients off of these variables here, we can find that our normal vector, I'll write that in vector notation, is actually equal to 6, 3, and 2. Okay, so we have our normal vector now, and we can find the magnitude of this. So let's see, the magnitude of N would be 36 plus 9 plus 4, and that will be our magnitude, or a little bit better, our magnitude of the normal vector. So now we've got, I'll put a box around these, we've got our normal vector in component, or rather in vector form, our magnitude of the normal. So we have this and S, we just need P. So where P is a point on the plane, let's find a point on the plane. So where does X, Y, and Z, what values make this equal to 12? So we need a point on this line, and we can say that this point, somewhere this is true, we can say that point is 1, 0, and 3, it looks like. So if we had 1, 0, 3, we'd have 6 times 1, which is 6, plus 0, plus 6, 2 times 3, and that would equal to 12, so this would be on the plane. Or on the plane, yeah, on the plane. This is the plane equation, not the line. So we just took a point on the plane by solving when this is true for all the variables here. And so we've got, the point is x1, y is 0, and z is 3. And so now we've got a point here and our s, and our point not on the line. So we've got our point on the plane. We've got a point on the plane and not on the plane. So PS would simply be the component subtraction, and that's a vector, of the components of P from S, or rather S from P. So this would be 5 minus 1, comma, 0 minus 0, and 0 minus 3. And that'll give us 4, 0, -3. So this is PS. And so now we have everything. We have n, magnitude of n, p, and we have ps as well. So now we've got everything. So we just need to do the dot product of these two. So I'll go ahead and evaluate n over the magnitude of n, which is going to be, the magnitude of n will give us 6, 3, 2, and then it'll be over 7, 7, 7. And that'll be our new vector here. And yeah, that's how we do. And then we'll do the dot product of these two. So p dot product of, ps dot n over n, and I'll worry about this in magnitude later, is going to be 6 over 7 times, where's my p? I should have, there, right here, or my ps rather, which is here, and n, so 6 over 7 times 4, so 6, 12, 24, over 7, plus 0, and then minus, that should be 3 times 2, so 6 over 7. And actually, because that's a dot product, that should be, we should just add this. And so that will be 24 over 7 minus 6. 24, that's 4 is 20, and then that should be 18. So 19, 20, 19, 20, yeah. Over there, and that is just going to be, I believe, the magnitude of that should be 18 over 7, and let's check. Perfect. So we took the magnitude of this. In this case, the magnitude, because we have a scalar, is just our absolute value. So it goes from 0 to positive, or from negative to positive, obviously because you can't have a negative length. So 18 over 7 would be the distance from the point not on the plane to the plane. So let me just run through quickly what we did here. We said we have an equation and a point not on the plane. So we labeled that S, the point not on the plane. We looked at our plane equation and found the coefficients of the variables and identified those as the components of the normal vector. We then took the magnitude of the normal vector, evaluated the normal vector over the magnitude of the normal vector, solved for this plane equation to find a point on it, took our p of s vector by calculating the subtraction here of the 2 points, so the components of s each minus the components of p, and then we took a regular dot product. And that gave us, once we did the magnitude, which is the absolute value, our distance. So that's it, and I hope this was helpful to you, and I'll see you next time. Let me know.
I'm gonna?
Let me know when you start.
I already started.
Okay, I can edit this out. Perfect. So if anything messes up, just leave it on, and I'll keep talking, and I'll cut it later.
Okay.